begin with linear models here. Constant function. What does the word constant mean? Yes. I disagree. Zero slope, which means the line that we are drawing looks like what? A horizontal line. So here, y equals -5. 1, 2, 3, 4, 5 is a horizontal line. Constant functions means m is 0, 0, excuse me. Okay, what would be a constant function? Actually, it's technically not a function, it's a relation. If I had something like this, what would the equation of the green line be? X equals 3, and what would the slope be? No, undefined. All right. We'll get to this later, but undefined slope represent our asymptotes. So things that you cannot cross or things you can approach but cannot touch will be defined as our asymptotes. And we'll get to that later on. Okay, linear functions, historically, we write them as y equals mx plus b. The base function or the identity function for a line is just y equals x. M represents the slope, B represents the intercept. So in the identity function, your intercept is 0, your slope is 1. This is the identity. Am I? Oh, okay. That's cool. I'm not intending to, but that's all right. Okay, so here when we have an equation here, 3/2 x plus 1, that plus 1 is your starting point. Where is it? I-intercept of 1, so this is 0, 1. And then my slope is telling me I'm going where? 3 up and 2 to the right, because it's positive. 3 down, 2 to the left, 3 down, 2 to the left. So this is what my line looks like. Okay, let's talk a little bit about slope. What's the definition of slope? You just shout it out, it's fine. Okay, rise over run. What's the mathematical definition of slope? Parneet. What's the mathematical definition of slope? We did this 2 days ago. I want an equation. Yes. Fantastic. Yes. It is the change in the height or change in the rise over the change in the x. A short way to write this is little triangle. Do we know what the triangle is? Yes, but do we know what it is? Delta. See, I'm half Greek, and so math and physics are basically my second language because we do all these symbols. This is the small letter delta or the small letter d, but delta means change in. Now, I want you to look at this equation. I'm writing a little bit large, but you can maybe not write as large as I am here. Looking at this equation, if I want to rearrange my slope equation into y equals format, what would be my first step? I want to rearrange this equation, but I want it to be in y equals something format. How would I rearrange it? What do I need to move and how would I do it to get the y's by themselves? Yes. Yes, multiply the delta x or the bottom piece to m, so put it to the other side. This will bring the equation to look like this. That is, yeah, slope point form, exactly. And if the points that we're choosing is our y-intercept, where x is 0, or one of the x's is 0, then we can further rearrange it to this. And that brings us back to slope-intercept form. Okay, so we have a slope formula, we have a line formula. We can always manipulate them, rearrange them to solve for the thing that we want. This equation is going to be your saving grace in this course. We are going to use it every day, over and over and over again. But the way that we rearrange it will look different as we go on and as we get more complicated. But the essence of calculus is slope. That's the whole course in a nutshell. Different ways that we calculate slope. All right, I'm going to skip over the regression stuff for now. So let's go to our next category of functions, which is polynomials. Polynomials can be written as a function p. And you'll notice this notation, this will come out a lot. The a sub n is the coefficients. And our leading coefficient is always the number in front of the x with the highest degree. So these exponents here are the degree of the polynomial. All right, the n's just represent how many we have. So n is a placeholder. If n is 2, then we have degree 2. That means we have 2 coefficients, the first one and the second one as we go forward. Yes.
What does subscript?
It's a placeholder. So this tells you how many coefficients you have. A sub 0 we refer to as the, not the coefficient, the constant. The last term that does not have any x's with it is the constant. Yes, sir. It's just filling in the blank. So there's a bunch of a's and x's in between. So for example, if n is 10, then this would mean this is a degree 10. This is degree 9. 8, 7, 6, 5, 4, 3, 2. Here's the 2 and the 1. So just showing that you can have as many degrees as you want. We're just not writing all of them. Okay. I want to erase that bit there. I don't want to put numbers in here. Coefficients, degrees, constants. Hopefully that is review for you. Here are graphs of various degrees. What is something we look for when we have a cubic? What is the basic shape of a cubic? Yes. Up, down, right? We always start, if it's positive, going from your left end down, and it comes out like this, right?
Yeah.
Okay, what about a quartic?
Up, down.
Okay, what's the basic shape of it?
It's a W.
A W, something like this. Okay, and what's a 5 look like?
Up, down.
Yeah, a quartic is basically 2 quadratics, right? Here's 2 parabolas. So a quintic would be up, down twice. Would be like 2 cubics. Those are odd functions, right? Even functions end up with W shapes, and the squiggles between the W's vary depending on the degree. And then odd degrees end up with a squiggly line, essentially. Okay, so those are our various degrees. And I should probably write this word if it lets me scroll. Here we go, quintic for 5. Quintic. Yesterday we talked about symmetry. So when we talk about power functions, y equals x, although we know it's linear, this is technically degree 1. It is a polynomial. Degree 1, right? This is degree 2, this is degree 3, this is degree 4, and 5 over here. The basic shapes for them, we've already just kind of covered. But looking at the base form of each one, no transformations, no reflections or anything like that. They will all be centered at the origin and have these kinds of shapes. A quartic will actually look like a quadratic, just a little bit fatter sometimes. And a quintic will look like a cubic, but a little bit more squished down. This is without having any kinds of coefficients or constants, changing the base of the equation. So you can also see when we talk about symmetry, is degree 1 is odd, even. Yes, sir. Ooh, yes, you are. No, he's right. Oopsie. Let's erase. It would be skinnier. You are right. Right? Because 2 to the power 4 will give you a higher y value than 2 to the power 2.
But then when it's the value of x is less than 1, it would be squished down, wouldn't it?
Yeah. Let's just pretend we haven't zoomed in that far. Depends where you've zoomed in. Okay, so odd degrees will give us an odd symmetry. Hopefully that makes sense, right? Even degrees give us even symmetries. What do we call this equation? The one I just circled.
The linear.
Yes, and? Nope. Go to the previous page. What do we call y equals x?
The ideal.
Nope. Identity. Very good effort though, guys. Lots of I words. This is the identity function. Okay, also from now on, I do not like to write. That's why I'm a math teacher, not an English teacher. EQN is equation, FN is function. I will not be writing the whole words out. They take too long. Okay, some things to note about polynomial functions. Y equals x to the power n for n whatever degree. When n is even, we have an even function. When n is odd, we have an odd function. We just talked about that. But also, n is increasing on the graph. The graph becomes flatter at 0 as the power of x becomes greater than 1. The absolute value of x becomes greater than 1. So as we get x to the power, excuse me, x to the power 4, 5, 6, as you guys were just talking here, the closer you are to 0, the flatter it becomes, but the further out you get from 0, the steeper it becomes. Yes.
So basically just going back to the quartic function, how like when we zoom in at like 0 to 1,
Yeah.
it's flat, and then afterwards it just becomes very steep.
If I were to redraw this, okay, let's do it a little bit. You don't have to redraw it on yours, but just as a visual thing. Let's say that the quadratic looks like this. The quartic would look steeper on the arms, fatter in the bottom, and then steeper in the arms, right? So the closer you are to 0, the flatter it is, but as you get greater than 1, it becomes steeper. It shoots up a lot higher. And it's the same with all of the functions as well. All right, skipping over the next regression question, we're going to go to the last two categories here, square root functions and reciprocals. For these basic catalog of functions, I'm expecting you to know key points. For example, if we have y equals the square root of x, what are some key points we should always know for a square root function? Joked. 0 at 0, 1 at 1.
Y at 4. Y at 4x.
So 4, 2. So 2, 4.
Yeah.
Okay. Yes. And it looks essentially like a sideways parabola. Think of the x squared function. 0, 0, 1, 1, 2, 4. Same points, but inverse, right? Like it's flipped over to its side. It doesn't have a negative. Ideally, in theory, it does exist, but mathematically we cannot plot it because we can't take the square root of negative numbers. But essentially, root functions are the inverse of power functions. So here, when I have the cubed root, think of what are some, excuse me, key points of a cubic function. What would be some key points? 0, 0, 1, 1. Sure. Go positive. 9, 3. Yes.
No, 8-2. Because 9-3 is just multiplying by 3. So
Great
that's square.
catch. 8, 2. Awesome. Right. And so if I were to mirror it of what it could look like if we took, actually with cubics, we can, right? We can take the cubed root of -8. This one actually does allow us to go backward. So you end up essentially with a cubic function, but on its side. So roots are the inverses of quadratics. If you understand how to graph a quadratic, use that knowledge and just essentially flip it on its side. What would it look like if it were on its side? Okay. Okay, let's look at reciprocals. Reciprocals is 1 over something. So now we have asymptotes. Brittany, where's the asymptote for 1 over x? Right. X cannot be 0 because then we would be dividing by 0. And y cannot be 0 because there's nothing we can do to the function to make it equal 0. The only way we can make something equal 0 is by dividing or multiplying by 0. We can't do either in this case. So we have asymptotes where the green lines are. What are some key points of a 1 over x function? Go ahead, shout them out. 1, 1. -1, -1. Goes on forever in which direction? What are we getting close to? So as I go to infinity.
So in y direction, it's going to be infinity, in x direction.
Yes, in the y direction up and in the x direction to 0. Yes. We're going to get infinitely close to x and y. So in the vertical, as we get larger in the y, we get closer and closer to the y-axis, but the value is infinite. And in the x, as we go off to infinity, we get closer and closer to the value 0. Okay, what about x squared? What are the asymptotes here? What's your non-permissible value? Okay, so x cannot be 0, so that automatically means, oh, sorry, not that. Automatically means I can't touch the y-axis. If x cannot be 0, we cannot touch that line. Can I make y 0? Is there anything I can do to that function to make it equal 0? No, so then I cannot touch this axis either. So my axes, my asymptotes are still the x and y equals 0. And we call the vertical asymptote, because I don't ever want to spell it, a VA, and the horizontal one, an HA. Okay, what would be key points here? Yes. Okay. So my left side would kind of look similar. Sorry, my right side would look similar to the original, 1, 1, right? But it would be steeper, right? I can't do it right now because my graph is small, but it would be steeper, right? 1 over 2 squared would be 1/4 instead of 1/2. So we're getting closer to 0 much quicker, and we're going to infinity much quicker. What happens if I say x is -1?
We're going to be in second quadrant.
Right. Rather than being in the negative quadrant, number 3, we are going to be in the positive quadrant, number 2, because of the squared. Are we pretty comfortable with that? Is trigonometry everybody's favorite? It's coming. It's my favorite. I will say, as I was planning to teach calculus, I got very, very excited when I remembered that we're going to do trig. Trig is awesome. Okay, so rational functions. this is where we have kind of weird looking graphs and we have asymptotes everywhere. How would I find my asymptote? Remember, asymptotes are non-permissible values. Where would I look to look for non-permissible values? I would look in the bottom. Okay, so can you tell me, let's factor this. What is the bottom factored? X plus 2, x minus 2. Okay, so that tells me I have an asymptote here and here. Can I do anything with the top? It's a quartic, not a quadratic. Not much information here. So I'm going to leave the top as is. 2x to the 4 minus x squared. Can you guys grab a calculator? Let's do a couple of table of values. Whenever you're not sure about an equation or about a function, it's good to take some values close to the asymptotes on the left and the right. So we know that 2 and negative 2 and positive 2 are asymptotes. So let's check the values. Let's do -5, -3. So 2 points on this side of the asymptote. Let's do -1, 0, and +1. So this part in between the asymptotes. And on the other side of the 2, let's do a 3 and a 5 as well. Okay? Now, I don't want you to type this out over and over and over again. So I'm going to pause my recording and show you how to do this on a calculator.